Hello everyone. Today is the 67th day of Leetcode 75 challenge. Let's begin with the 67th question. Question 338 counting bits. The level of the problem is easy. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given an integer n and you need to create an array answer of length n plus 1 for each integer I where I is from 0 to n. Okay. Determine the binary representation of I. Count the number of 1 bits in that binary representation. So basically, what they are trying to say that if n is suppose 4, then the array size has to be n plus 1, right? So it will be 0, 1, 2, 3, 4, right? N was 4, size of the array is 5, correct? Now they're saying that for each integer I from 0 to n. So basically for 0 to n, n means n is included in this case, n is 4 here, so that means 0 to 4. Determine the binary representation of I. Count the number of ones in that binary representation. Store this count at index I in the answer array. For example, what is the binary representation of 0? It is 0, right? And how many number of ones are there? Of course, 0. So we will place 0 here. What is the binary representation of 1? You could call it as this way, right? How many ones are there or set bits are there? It is only 1, right? Okay. Binary representation of 2 is how? It is 4 to 1, right? It is 0 1 0. So number of ones are only 1 here, right? Binary representation of 3 will be like 0 1 1. How many ones are there? 2. So we will write 2 here, and 4, binary representation of 4 is this way, right? If we place it that, so number of ones is only 1. So this is what we have to return at the end. Return the answer array after processing all the integers from 0 to n. Fine. Now, so the question also says that n log n is the expected time complexity which can be taken by anyone, but the expected follow up, which is the main one, is O of n time complexity in which we have to solve this particular problem. So we will look at both of the solutions and how we're gonna do it. Now the time constraints are n starts from 0 and goes till 10 to the power 5. Okay, so I hope you understood the problem explanation. Now let's move to the next slide. Now let's understand the input output explanation. Here you could see n is 2, right? So n plus 1 will be, array size would be this way, correct? How many ones are there in 0? 0. How many ones are there in 1? It's 1. How many ones are there in 2? 1, right? So this is what the output is. When n is 5, the array size will be 6 basically, right? How many ones are there in 0? 0. 1, 1 in 2, 1 in 3, 2. In 4, how many ones are there? 1. In 5, how many are there? 2, right? So this is the binary representation or the expected output. So the input output explanation was pretty straightforward and easy. So I hope you understood the input output explanation. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's start doing by understanding the goal first. So we are given an integer n. We must create an array answer or whatever name of length n plus 1, as we have already seen before. For each integer I, where I is 0 to n, we count the number of ones in its binary representation. Okay. For example, if I equals to 5, the binary is 101, right? There are two ones. The brute force. Okay, so this is the what we understood. So what could be the brute force solution for it? As we have already understood the goal and the solution what we have to bring to the table, the brute force could be, since we have to iterate all the binary representations, right? For 5, it will be 0, 1, 2, 3, 4, right? 5, right? So therefore, a for loop will go from 0 to n. N is inclusive, right? 5, because you need the binary representation of 5 and the ones present in it. Now there are two ways to do it. One way is a built-in function given by Python named as bit count. If you throw any integer within this function call, it will return the number of set bits or number of ones in the binary representation of the particular integer. Okay, so this takes time complexity log n, and since we're gonna iterate from 0 to n, that will take another n. So the time complexity for that becomes n log n. Another way is, for each number, repeatedly divide 2 by using shift bit shifting. For example, if you know, suppose this is the binary representation of what, uh, 1 2 4 8, right? It is a binary representation of 10. So what you do, you try to divide this. If it is an odd number, you increase the count, otherwise you shift to the right, and when you shift to the right it becomes this. Then you divide this particular binary bit by 2 to check even if it is odd or even, right? If it is odd, you increase the count, and again you shift it, it becomes 1 0. Then you check again you shift, then again you count, right? This is another way, and this will also take n log n time complexity, because dividing and checking takes log n time complexity for each integer, and n time is taken by iterating from 0 to n. Okay, so I hope you understood the brute force solution, which is expected one, but they are looking for much more optimized one of O of n time complexity, right? So we need a smarter approach. So let's try to visualize the process first. Okay, I will bring down some of the numbers here. Till here I've written till 4, right? Let me write a few more. Suppose 5. 5 is what? 101. Or let me do one more thing. I should write, no, it's fine. 6 is what? 6 is 110. 7 is 111. Representation of 7 basically. 8 represents as 100. 9 represents as 1001, and 10 is represented as 1010. Fine. Now if you here you can see a pattern. Suppose let's take 4 here. Okay, 4. The count for 4 is 1. Number of ones only present is one time. Now if you divide 4, take the half of 4, which is 2, right? When you come to 2, you see that binary representation is 10, and the count of 1 is also 1 here. Fine. Now let's take 8. Okay, so if you can see, come and see an 8, you will see that there is only one present in the binary representation of 8, right? So if you have observed something, if you go for 16, let's go for 16, right? So what is the representation of 16? It's 16 8 4 2 1, right? So this is how 16 is represented. So how many ones are there? Only one. So from here we can conclude that for the even integers, if we take the half of it, right, it will always give the same set bit, count of set bit, same count of set bit or ones. Okay, suppose let's take 10. Okay, if you can see here 10, 10 set count is what? It's 2, right? Half of 10 is 5, and we can see that the set count or 5 is or ones is 2, same as 10, right? If we have taken 20 also, let's take 20. Representation of 20 is how? 16 plus 4 is gives 20, right? How many ones are there? 2, right? And 20 is half is what? 10, right? For 10 also we have two set bit counts. So from here we can conclude that if we have n, then when n is divided by half, the set bits for n and n by 2 is same. Okay, so how this actually works is that I will explain that later part. Let's understand for the odd numbers now, right? Till now we have just seen for the even numbers. Let's take 5. Okay, now when 5 are divided by 2, what we get? We will get 2.5, right? That does not make any sense, so it will be boiled down to 2, right? But the two number of ones, count of number of ones in 5 is 2, right? And count of number of ones in 2 is 1. Does not match, but here it is a mathematically logically or mathematically solved equation that when n is divided by 2 we have to add 1 to it. So when we do that, what we get 3. Number of count of ones in 3 is how many? How much? It's 2, right? So we can see that count of 3 and 5 matches. Let's take another example. Let's take for the 7. 7 divided by 2 plus 1. How much we get? Gives me 3, right? Count of 3 is how much? Count of 3 is 2, right? So it's 2 plus 1 gives me 3, right? That is similar, or that is exactly same the count of 7. So how this odd number works is that it's basically, suppose result. we could say result of n by 2 plus 1, right? So this gives me the bit set bit counts of the n by 2, and in that we just add 1. Okay. So what we understood from all of this part, we understood that we can reuse previously computed result instead of recomputing from scratch. So let's understand how it works, right? We understood the intuition, how we understood the visualization process, how we're gonna do that. Now let's verify this statement. So we can create an array bits count, right? We will create an array named bits count of n plus 1 size. Suppose let's take the example of 5. Okay, so it will be 0 1 2 3 4 5, right? Size is 6 of the array. Great. Then we know that bits count, right? Bits count of 0 will always be 0, right? We will add that 0 here. Great. Now we'll start a for loop from 1 to n plus 1. Why n plus 1? Because in Python, when we write range, this part is inclusive, but this part is exclusive, right? To make this inclusive till n, we have to write n plus 1 so that our range considers the n. This is pretty much understandable, right? There is nothing much to explain in that scenario. So when we do that, we check if it is even, right? If the I is even, what we will do? Bits count, suppose, equals to, let me write it properly. So for loop will go from 1 to n plus 1, and we will check that if I is even, then just nothing, just bit count of the I, right? Suppose I is 1 right now. So we need the number of ones for the particular I, right? Suppose I is 1 right here. So what will happen? Bit count of I by 2. That's all. Now, since here I was 1, suppose we know that for 1 we have 1, right? Suppose we have 2, 2 divided by 2 gives me 1, right? So when we go back, so bit count of 1, here we will be having 1, right? So at index 1, what is the count of ones? It is 1, right? So this will get filled with 1. Fine. Suppose if you go for 3, what will happen? Bit count of I, which is 3 right now. So bit count of 3 by 2 is what? It's 1, right? Plus 1. Bit count of 1 is what? It's 1 plus the 1 here gives me 2. So in 3 we will put 2. And what is the binary representation of 3? It's 0 1 1, right? So this is how it will keep on going, as I have already done. If even is there, bit count should be this way. If it is odd, bit count should be stored in this way, right? So we are just trying to get the previous result or the previous number of bit counts of that, right? That is already proved. For the half of even, basically, it is exactly the same. But for the odd, we just have to add 1 to the particular result. That's all. And there could be a base case, which I have already explained, which is if bit is 0, add it 0, right? That's all. What we figured out? We figured out that brute force takes n log n because we count bits for each number individually, which is accepted, but the follow up is much more important to do, right? So we use the relation count bits even divided by 2 and count bits odd divided by 2 plus 1. We can compute the result in O of 1 for each, but total time taken. Doing this operation takes O of 1 time, but total time taken will be O of n, right? Which is our follow up requirement. So I hope you understood the intuition explanation. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're gonna solve it. So first and foremost, we will start by handling the base cases. First, we will say that if n is 0, the number which is given to us is if all it is already 0, there is nothing to be done, right? We will just return the array which we created, which is basically empty. Only number 0 exists for binary is 0, so count is 0. Definitely correct. Now initialize the result count. Now we will create this bit count array, or we will initialize this bit count array. How? This way. Bit count equals to 0, we filled with 0 with n plus 1. So the bit count will already have 0 within it, right? This is how it will work. Now next, we created this. Now we set the base case that if it is not a base case, or you could say a base case. If in bit count of for 0, it is always 0, right? So we have to set it. So I have already set it here. We need a place to store results and starting values to build upon for the larger numbers. Okay. Now at step 3, we fill using the recurrence relation. We could say we am calling it a recurrence relation, but it is not a recurrence relation. It is just you could say mathematical understanding. Okay. So if you could observe here, we'll try a loop from, it will be like this, from 1 to n plus 1. Okay. And if I is even, if I mod 2 equals to 0, then we just store bit count equals to similarly bit count and divided by 2, right? And else it is odd, right? So we will do bit count n by 2 plus 1, right? We do that. So even numbers are just right shifts of smaller numbers, while odd numbers have the small count as the right shifted version plus 1 extra. This is the concept, right? Now at step 4, after completing this iteration, we just return the bit counts. That's all. Okay. So the approach is pretty simple and straightforward. Okay. So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. If you could see, I have initialized the bits count array with 0 and plus 1. Have taken a base case if n is 0, return bits count. Okay. After that, we run a for loop from 1 to n plus 1. If it is an odd, if it is an even, we just take the previous count of that particular half of n by 2 and store it here, because it will be same every time. But for the odd one, we go for the previous number and we just add 1 to it, right? And at the end we return the bits count. The time complexity for this is O of n. As you can already clearly see that we're iterating the array only one time, that is also size n. Okay. And space complexity is n plus 1, because the array size is equals to n plus 1, which we have declared as per the question requirement. So I hope you understood the code explanation. Now let's move to the next slide. Now since we have the understanding of the code, let's look at a dry run of the example. And for our better understanding, I have also brought down the code here. Okay. So let me draw the array of n plus 1, because n here is 5, right? So it will be 6 size array. 0, 1, 2, 3, 4, 5, right? Size is 6. Great. Everything is initialized with 0 as per our question, or the code you could say. Now, since here n is not 0, right? So we will go from 1 to n plus 1, because count for 0 is already 0, which we have initialized. Now we started with 0, now we started with 1. 1 is an odd, right? That is pretty clear. So we will come to this particular scenario and we will check the bits count of n by 2. 1 by 2 is 0, right? So what's 0? Value of 0, index 0, you could say index 0 is 0, right? So to that we add 1, and so this gets updated to 1, right? Correct? Fine. So now this iteration complete. Now 2. Now 2 is even. Now 2 divided by 2 here gives me 1. Okay. So we will just update this with 1. Now we move ahead. Now 3. 3 is an odd. So when we divide 3 here, 3 divided by 2 gives me 1, right? For bits count of 1 is how many? Number of ones is 1. So for this we get 1, then we add plus 1 to it, so it becomes 2. So we store 2 here. Then we move ahead, and we have 4, right? Or 4. 4 is an even number. So 4 divided by 2 gives me 2. So for this bit count of 2 and index 2, we have 1, right? So 1 will be placed here. Great. Now we'll move ahead. Now it's 5. And since it is an odd number, 5 divided by 2 gives me 2. The bits count of 2 is how much? It's 1, right? 1 plus 1 gives 2, right? So the bits count, number of ones for 2 is 5 is 2. So you could see that our array is modified to 0, 1, 1, 2, 1, and then 2, right? Which is our expected solution. Yes. So I hope you understood the dry run. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the code, and also the bit manipulations concepts if you don't know. And after that, do a dry run by yourself for 2 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. So let's start by initializing the bits count array of 0 size and plus 1 for bit. Then we will do if n is 0, just return bits count for I in range from 1 to n plus 1. If I, or rather than calling it I, let me call it as num for much clear understanding. If num is even, then bits count, that num will be bits count num by 2. Okay, else if it is odd, it will be the same thing. Okay, just we will add 1 to it and we will return bits count. Let's try submitting for the sample test cases. Now let's finally submit our solution. So we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.